Hello everyone, today we're going to talk about element number 5 on the periodic table, boron. Boron is relatively abundant on Earth. It's found in the lithosphere along with carbon, nitrogen, oxygen, hydrogen, fluorine, magnesium, sodium, aluminum, silicon, phosphorus, sulfur, chlorine, potassium, calcium, titanium, iron, copper, nickel, zinc, gallium, germanium, arsenic, selenium, bromine, and all those various other elements that are presented here on the relative abundance scale on Earth. Today we're going to talk about the specific metalloid or metalloid, as people pronounce it differently. It's called that because it has the properties of both a metal and a nonmetal. That means that it can be both conductive and insulative at the same time based on how it's changed, altered, or presented in various things. In fact, in semiconductors, we dope them with boron and phosphorus because phosphorus has 5 outer valence electrons and boron only has 3. And because of that relative difference, we can use that to create a p-n junction, which simply means that there's a relative potential difference and there's a field that can be used in electricity to be able to turn circuits on and off, or to be able to put them in a way where they can produce processes that wouldn't be able to exist otherwise. So we're going to talk about boron. Let's begin. Boron is found in a city known as Boron in California. It's named after the element. The element is not named after the city. In fact, in the city, they don't have the pure refined element boron. They have the oxide of boron known as borax. Borax was carried by a 20 mule team out from boron, and that's why we have this box in this image labeled 20 mule team borax. All natural since 1891, because that's the location in California where it was carried away from. The molecular formula for borax is Na2B4O5OH4 multiplied by 8 moles of water, which is H2O. The molecular formula for boron is presented below. It consists of sodium, boron, and oxygen, along with hydrogen. So essentially, if you rearrange these, it's just Na2B4H4. Rearranging them, we see that it's basically water combined with sodium, boron, and hydrogen metals that are oxidized by oxygen. Metals are usually oxidized by the name carrier oxygen and by halogens on the periodic table such as fluorine or chlorine, which just need a few more or just one more electron sometimes in order to complete their shell, and that is what makes them so reactive with metals that are willing to give their electrons away and oxidize in the process. Borax is one of those various metals or semi-metals that is oxidized by oxygen, along with other metals together. So boron has 5 protons, 5 neutrons, and 5 electrons. It has 3 valence electrons, which allow it to perform interesting chemistry in semiconductors or in PNP junctions, which are similar. The reason that they work for us well is because of their 3 valence electrons. Since boron has 3 valence electrons and silicon has 4 valence electrons, it can be used to dope. That's the appropriate term for inserting boron and a different type of element that contrasts to boron. In this case, it's arsenic. It can be arsenic or phosphorus since they are in the same group and share the same amount of valence electrons. They can be used to dope silicon with and contrast it with the boron added silicon. What we see here is that there's a relative difference of electrons. One side of the silicon will have what is called a hole and one side will have an electron. And what happens here is that the silicon with the boron on its side will have a lack of electrons relative to the silicon with the arsenic or the phosphorus on the other side, because it has one more relative electron than the silicon has, and that allows it to have relatively more energy than the other side. And this difference in energy is what allows us to be able to utilize this in electrical currents and electrical circuits, because the fact that they have different potentials allow electricity to flow only in certain ways or in certain directions when we want it to, and that creates small microscopic switches that we can turn off and on super easily that don't require our manual input at all times. And that's what allows us to perform complex tasks via computers, because the silicon chips are able to relay a message in the form of zeros and ones by turning off and on. The computer recognizes the 0 as off and 1 as on. And thanks to these boron doped silicon chips, we can perform these actions through the computer and give it life in that way. So once again, boron is used in silicon chips due to its relatively low valence electron count when compared to arsenic or phosphorus, which has 5, which is 2 more than it has. Here's a visual demonstration. 3 arrows for 3 valence electrons, as we were discussing. Boron has 3 valence electrons, and that's why it's essential in PNP or PN junction chips. In this case, this is a PN junction, as stated here by the P and the N. The P simply indicates that it's a positive side, and the N indicates that it's a negative side, because there is a relative positive charge on this side because there is less electrons than on this side. And since electrons are negative and there are more electrons on this side is relatively negative, and since there are relatively less electrons on this side is relatively positive. And moving up here, we can see that there is a town in California in between Bakersfield and Barstow called Boron. Again, that's where borax is extracted, and again, borax is just an oxide of boron. So if you have trouble distinguishing between borax and boron, just know that boron is the main element. It's the raw element with 5 protons, 5 neutrons, and 5 electrons. Rarely is it seen in its pure crystal form. It's usually found in compounds or oxides, and that's why we find it as borax, which again is sodium, boron, and hydrogen combined with oxygen. You remove the oxygen, you essentially get the pure metals. Eventually you can get to pure boron in that way. But usually in nature, like when we're mining metals, we find them as oxides. The only metal in nature that is not found as an oxide is gold, and that's why we value it and treasure it so much, because of its non-reactivity even in nature. So we're going to take a look at group number 3 because boron is the beginning of that group, and we are eventually going to cover all of the elements in group 3 along with all of the elements on the periodic table. So since boron is the beginning of this group, we will start with it and see how this group eventually evolves into what we call Nihonium. Group 3. Most of the elements in group 3 are metals. They are less reactive than group 1 and 2 elements. Most group 3 metals react with oxygen and water, forming ionic metal oxides and hydroxides. And that's why, as previously mentioned, we find borax as an oxide with other metals. It's an oxide with oxygen and hydrogen, as the book mentions. A metal oxide is simply a metal, as I mentioned, with oxygen combined. And hydroxide is oxygen with hydrogen. Usually it's what forms bases when it dissociates in water. The physical properties of group 3. Most of the elements in group 3 are shiny metals except boron, which is a dull nonmetal. Due to the quantum mechanical properties of boron, its net electrons do not as a whole emit light in a shiny way like the other elements in its group, such as aluminum, gallium, indium, and thallium. As described here, pure aluminum is silver colored. Gallium melts slightly above room temperature and is also silver colored. Pure indium is soft enough to carve lines into it. The reason it's called indium is because of indigo, the color blue. Its line emission spectrums emit the color blue predominantly, which is why it's called indium. Fun fact. We'll eventually cover that. And pure thallium is kept in glass vials to prevent it reacting with air. It must oxidize very quickly for it to be kept in a vial like that. So group 3 has various shiny elements that emit light, except boron, because it doesn't have enough net energies in its electrons to emit light in that way, and so it absorbs it. And so what we see at the macro scale is a dull, relatively darker version of the element. The final element that is also included in group 3 that we do not have a picture of because it's so radioactive, its half-life being only 20 seconds, which means that if you had 100 grams of this element, in 20 seconds you would have 50, and in 20 more seconds, which is not even a minute later, you would already have 25, and then you would have half of that just shortly after a minute, and not even 5 minutes later you would have so little of that element that it would essentially be gone in your perspective. And if you weren't already gone as well, the element would have already obliterated everything around you, because the thing about radioactive elements is that they are so relatively unstable molecularly that their particles fly and eject at nearly the speed of light which causes them to interact with everything and speed it up at that velocity as well. And radioactivity, what we detect in a Geiger counter, that little beep 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 as we get closer to radioactive materials or locations, that occurs because particles are hitting the detector, and that causes an interruption in the connected speaker that's connected to electricity. The changes in the electrical voltage is what causes the changes in the speaker. And in that same way, if we had this final element, it would be ejecting so many particles per second that it would literally obliterate everything around it, and it wouldn't last for long. So even if we did manage to create a sample, we wouldn't be able to contain it or observe it for long because of the nature of its decay and radioactivity. Described by the book, it says, Nihonium at the bottom of group 3 is an artificial element that can be formed when scientists collide zinc and bismuth atoms together. So those are the atoms that are used to create this element. Bismuth and zinc, which are two elements that we will eventually talk about. Bismuth is radioactive. It's the first element on the periodic table to be radioactive. Its half-life being longer than the universe. Zinc is used with it. We will also talk about that metal. It's not part of the group, but it's used to create this element in this group. Nuclear fusion occurs, and the larger atom that forms is the element Nihonium. Moscovium can also break down into Nihonium. So if an element could break down into another one, then that means that the previous element that it was before is greater in mass than the one that it becomes. Even without knowing the atomic number of Moscovium, I could already tell you that Moscovium is heavier and has more protons than Nihonium, because according to the book, it breaks down into Nihonium. Again, if you want to be able to tell if an element has a greater atomic number than another one, just see if it breaks down into that one, and then you can already conclude without even looking at the periodic table that it is an element with a greater atomic number than the one that it becomes to. If that sounds too complicated, and don't worry about it. It's not too big of a deal. You can always refer back to the periodic table to see how one element turns into another. Sometimes it can even go up because it loses a neutrino, and that can cause it to become a proton, and the addition of a proton from a previous neutron increases the atomic number, and although it's less relative atomic weight, its greater atomic number causes it to change its properties as an element. And an example of that is like carbon becoming nitrogen by losing a neutrino and one of its neutrons becoming a proton, becoming a version of nitrogen that's relatively less light, but is still nitrogen nonetheless. That's just one of the various examples for decay and alpha emission particles and stuff. We'll eventually cover all those small, minute details, but continuing on back to boron, we can see the net big picture and how boron pertains to this group. Being a semi-metal, it has the properties of both a metal and a non-metal. That's why we use it in diodes, and that's why we use it in silicon, because again, silicon is also a semi-metal. So let's get into boron with borax. Borax is, again, an oxidized version of boron. So, again, the molecular formula for borax is sodium, boron, oxygen, and hydrogen combined in a molecular way that they exhibit the effects at the macroscopic scale that we use them for. And that applies to every molecule and every element on the periodic table. So boron and borax, what's the difference? Boron is an element, and borax is an oxidized version of boron, which simply means that it's combined with another metal, it's combined with the metal sodium, it's combined with the metal hydrogen, and it's oxidized because it has oxygen. And anything that's oxidized doesn't need to have oxygen necessarily, as we saw with the chlorine video. It just has to be bound to one of the elements on the right side of the periodic table, which just need a few more electrons to complete their stability, and that's why they bond with metals, because metals give the electrons away and get oxidized in the process. Oxidation, it just means that you lose your electrons. Remember, oil rig. Oxidation is loss, reduction is gain. In the compound, the oxygens gain the electrons from all of these metals. Poor metals losing their electron. But The net result is that they're all a molecule, and that's what borax is. Boron is more boring than borax because borax is the whole team right there. Sodium, boron, oxygen, hydrogen, and boron is just B. There are various types of fusions of boron that can be used. Another compound of boron is boric acid. It's used as roach away to keep cockroaches at bay. Boric acid could also be burned under a flame. Light is just a visualization of an excitation of electrons. When electrons get excited to the point where they gain a lot of energy, they start to release some of it back, and what we see as light is actually the groups of electrons that are excited and are so highly energetic that they're now visible to the naked eye, and that's why we see a flame. In fact, any metal or anything that we burn that produces different colored flames, the different color is indicating the differences in energy levels that all of the electrons accumulate together when they are excited. The fire is the process of the electrons gaining the energy. It doesn't really matter if there's a fire or not. You can make an atom glow simply by adding enough energy to it. It's just that in our macroscopic world, we can't really add energy directly into electrons, like inject it into it, without having some form of flame or some form of fire, some form of already hot object that is already able to transfer that energy to them. The 20 mule team for borax is called that because of Boron in California, which we previously mentioned is between Bakersfield and Barstow. A useful application of boron in boric acid is for suppositories that women use in order to clear any yeast infections that they may have. So it's essential in that medical aspect. It's nice to know that they have a remedy for such things. Don't get boric acid and borax confused. In fact, let me clarify and present the molecule of boric acid so that we can distinguish them more easily. The molecular formula for boric acid is H3BO3, not to be confused with borax, which is a way longer, more complex formula. But at the end of the day, it's still something that we can comprehend. It's a combination of hydrogen and boron, which again is an alloy or an amalgam of two metals combined with oxygen, which simply means that this metal is oxidized by oxygen, and that's what makes it useful. So there's 12 uses for borax in this image that I will go over. So number 1, you can use borax to clean your toilet bowl. Number 2, you can use it to kill fleas. Number 3, you can use it to prevent weeds from growing. Number 4, you can use it to remove stains. Number 5, you can use it to scrub dirty pots and pans. Number 6, it's an all-purpose cleaner, so you can use it for various things. You can use it as a Windex if you run out of Windex or window cleaner. Number 7, it boosts potency of laundry detergent, so if you use boric acid, you can improve your laundry detergent. Number 8, you can deodorize your kitty litter, so if you have kitty litter, you can use boron. And number 9, you can use it to deter mice. You sprinkle some on the floor walls to keep them away. Number 10, you can use it to kill roaches, ants, and water bugs. Number 11, you can use it to clean your humidifier because humidifiers have water, so they tend to accumulate mold and other stuff that thrive on water, so you can use that to clean it up. And number 12, you can use it to shine your china. China is a combination of metals oxidized with oxygen. China is very delicate, so it's nice to know that you can use boron to clean it. These are the places that you can find borax for the previous applications mentioned before. You can find them in grocery stores, hardware stores, health food stores, and pool supply stores. They have so many uses that they're found essentially everywhere and anywhere. Again, simple uses for borax: stain remover, toilet cleaner, dishwasher boost, and they help preserve fresh flowers. We're going to go back into the history of boron and analyze and see how it got to where it got today. So just like every other element, fluorine and all the complex other elements such as the ones we're going to talk about, iron, potassium, magnesium, they all get oxidized, they all get clouded by other elements on the periodic table. But our goal here is to understand each element individually and be able to identify it from the periodic table, classify it, and feel like we can relate to it like you can relate to a good friend. And that's what we're trying to achieve by making all these individual videos, to try to familiarize you with each individual element rather than just have an intimidating periodic table looking at you and making you feel like there's too many elements. But we're doing this and we're trying to understand each element. And just like the people that we are going to talk about, each person was trying to understand each element as well. The first people who attempted to isolate boron only did it in a rudimentary way, so they weren't able to purify it fully. The individuals who paved the way to boron's purification were Louis Jacques Thenard, Sir Humphrey Davy, and Joseph Louis Gay Lussac. They were all from similar places. Their homelands were industrialized, which allowed them to utilize their minds to further expand on the scientific field and just for the fun of it be able to learn more about the natural universe around them. So these two individuals, Louis and Joseph, they were from Paris. So at the same time, simultaneously in 1808, they partially isolated boron, as well as Louis in London in 1808. So all of them were approaching similar methods in 1808 using borax or boric acid as previously mentioned in order to isolate the boron that was present within the compound itself. And that's why we talked about the compounds before we talked about the isolation. That way it just makes more sense. Back then, goldsmiths used to utilize boron in the form of borax as a flux for goldsmiths. It was useful for them, and the only way to get that borax was from Tibet in Lake Yamdak. That was the only source. That's how it looks like today. So thankfully these individuals initiated the progression towards the isolation of this individual element. So here we have the formula that these individuals probably used or interacted with, and here we have borax, the formula for borax, and water, and it's mixed with potassium, and the result is an impure form of boron. So extracted boron unpure form by heating borax with potassium metal. So although the boron wasn't yet fully pure, that didn't stop other individuals from trying to isolate boron and purify it. And the next individual that we will talk about in the isolation of boron is one we already talked about in the fluorine video. He was involved in the electrolysis of fluorine, which allowed it to become separate from its previous bond. If you want to watch that video, the link is in the description below. I will attach a link to the previous video as well as a link to the fluorine video because I am mentioning it in this video right now. Henry Moysen, the person that isolated fluorine, he got a little bit closer to the purification of boron, element number 5. I call him the chemical distiller because he was persistent in isolating the most complex and difficult element on the periodic table, and he was able to purify it and get it in its pure form. He was able to see it and he was able to interact with it without perishing in the same way that others before him tried and died, unfortunately. And that's why I call him the chemical distiller, because not only did he go for fluorine, but he also went for boron, and he was able to more successfully isolate it just 84 years later in 1892. It wasn't until 1909 with American chemist Ezekiel Weintraub who produced 99% pure boron by reducing boron halides with hydrogen. So this individual is able to isolate boron because he uses a halide version. As I mentioned before in the chlorine video and in this video as well, since boron is a semi-metal, it has the properties of a metal, so it's able to bond like a metal. It bonds with chlorine because it's an oxidizer, just like oxygen, just like sulfur, just like chlorine and bromine. So here we have the balanced chemical reaction. We previously talked about how hydrogen interacts with other things like a metal. So in this chemical reaction, hydrogen is self-oxidized and boron is oxidized by chlorine. What happens here is now that the hydrogen gets oxidized by the chlorine, becoming hydrogen chloride, and the boron now self-oxidizes just like the hydrogen before and just becomes metallic boron, which just stays together and clumps together. It has the properties of almost a gas, but it's not fully a gas. It just remains in a crystal-like structure because it can't fully fly into the air, but it has relatively more energy than the surrounding metals. It's shown by the properties that it has as a semi-metal. And that's the overall chemical reaction. So again, boron just changes its oxides, oxidizing itself. Hydrogen goes from being oxidized by itself to being oxidized by the previous oxidizer of boron, chlorine. And that's the overall chemical reaction. Today, what we do in general is similar to the way that we purify iron. Just get coke, which is purified coal, and we mix it with the borax, and the coal is similar to the boron in that it's a semi-metal and acts like a metal and exchanges oxides with the oxidized boron and takes away the oxygen and purifies the metals in the borax, one of them being boron, which is what we need and what we're purifying. So that's the overall process of boron. The winner of this Olympic race to purify boron is is equal Weintraub. He produced 99% pure boron. So other key details about boron is that boron is not easily produced in stars. It's produced in space when it's bombarded by cosmic waves. When carbon or other elements that are vulnerable to the cosmic waves are bombarded, they change their nuclei and alter into different types of elements. And the different configurations of protons, neutrons, and electrons creates a different elements. And so those cosmic waves rearrange all those configurations, and eventually one of those configurations result as the element boron. So here's a diagram that I use to explain how elements are made in stars. So 3 helium atoms fuse to give a carbon atom, and then the carbon fuses with another helium atom in the star to produce oxygen, then oxygen fuses with another helium nucleus and electrons to attain neon, and then neon fuses with another helium atom to attain magnesium. So it just skips around, and I found that very peculiar. But now that we understand that these elements are not created directly in stars, rather they're created through alternate ways in space and in other locations throughout the universe, it makes more sense as to why they act in the way that they do, because they're not created in normal stars, so they don't relate to the gases that are early on in the periodic table, labeled 1 through 10. So quick summary, boron may have been the key to the evolution of life on Earth. Unlike many elements which form in fusion reactions within stars, boron formed after the Big Bang by a process called cosmic ray spallation. During this process, colliding cosmic rays split the nuclei of atoms, causing fission. And that explains how boron is created. So that was Boron explained in 28 minutes or less. If you're interested in watching the previous video, it was on chlorine explained in 25 minutes or less. It's a video on the second halogen down after fluorine. It's very reactive, and there's a lot of compounds that it forms. It's similar to oxygen in that it oxidizes. I also have made a video on oxygen if you want to watch that video. The list is in the description below on all the previous videos. I've officially completed 10 videos on the periodic table, so we still have 108 to go, but we will eventually cover all of them. Thank you guys for watching. Make sure to like, comment, and subscribe. See you guys in the next one.